Welcome to Essential Mechanisms of Biochemistry. In this video, we take on oxidative phosphorylation. Let's get started. Embedded within the inner mitochondrial membrane, there are 5 remarkable molecular machines. Complexes 1 through 4 transfer electrons toward oxygen, and ATP synthase then converts the resulting proton gradient into the chemical energy we know of as ATP. Our goal today is to follow every electron and every proton from beginning to end. We begin with complex 1, the largest enzyme of the electron transport chain. Here, electrons stored within NADH first enter the respiratory chain. NADH transfers a hydride, that is, 2 electrons and 1 proton, to flavin mononucleotide, or FMN. Unlike NADH, which freely diffuses through the mitochondrial matrix, FMN is permanently bound within complex 1. FMN therefore serves as the first electron acceptor inside the enzyme. The 2 electrons cannot move together through the remainder of the protein. Instead, FMN releases them one at a time. Each iron-sulfur cluster accepts a single electron before passing it to the next cluster in the chain. The sequential relay prevents uncontrolled backflow while gradually moving electrons toward coenzyme Q. At the end of the iron-sulfur chain sits ubiquinone, also known as coenzyme Q. Unlike the iron-sulfur clusters, ubiquinone accepts not only electrons but also protons from the mitochondrial matrix. 2 proton-coupled electron transfer events convert ubiquinone into ubiquinol, or QH2. Because of its long hydrophobic tail, QH2 can now diffuse freely within the membrane to deliver its electrons to complex 3. Reduction of coenzyme Q does more than simply transfer electrons. It changes the electrostatic environment of complex 1, triggering a series of conformational changes throughout the membrane arm of the enzyme. These conformational changes alter the proton transfer pathways, allowing 4 protons to move from the matrix into the intermembrane space. There is also an important bookkeeping result here. During the citric acid cycle, every NADH that was produced was accompanied by the release of 1 proton. At complex 1, reduction of ubiquinone consumes 2 matrix protons. One of those is the proton carried by NADH itself, while the second comes directly from the matrix. This completes the proton accounting for NADH formation earlier in metabolism. Complex 2 is unique because it belongs simultaneously to the citric acid cycle and the electron transport chain. It is the same succinate dehydrogenase enzyme that oxidized succinate to fumarate. Unlike NADH, however, FAD remains tightly bound to complex 2. Electrons are again transferred one at a time through iron sulfur clusters while reaching coenzyme Q. Each electron transfer is accompanied by a release of 1 proton from the reduced flavin. Just as in complex 1, ubiquinone accepts 2 electrons and 2 matrix protons to become QH2. Thus, both NADH and FADH2 ultimately feed electrons into the same membrane-soluble electron carrier. Now, notice something interesting. The protons released when FADH2 is oxidized are immediately reused during reduction of ubiquinone. The net reaction simply converts FADH2 into QH2 without moving protons across the membrane. Complex 2 therefore contributes electrons to the chain, but does not directly contribute to the proton gradient. We now arrive at perhaps the most elegant portion of the electron transport chain. Ubiquinol carries two electrons, but cytochrome C can only carry one. Complex 3 solves this problem through what is known as the Q cycle. The first electron from ubiquinol travels through the risque iron sulfur center and ultimately reduces cytochrome C. Meanwhile, the second electron follows a completely different route through two heme B groups before partially reducing another ubiquinone molecule. At the same time, the two protons carried by the original QH2 are released into the intermembrane space. When a second QH2 arrives, the entire process repeats. A second cytochrome C receives another electron, while the partially reduced ubiquinone accepts its second electron and another matrix proton, regenerating a new QH2 molecule. Putting both halves together reveals the beauty of the Q cycle. The two QH2 molecules are oxidized, while one new QH2 molecule is regenerated. Overall, two electrons are transferred to cytochrome C, four protons appear in the intermembrane space, and two additional protons are removed from the matrix. Rather than pumping protons directly, complex 3 amplifies the proton gradient by redistributing the protons carried by ubiquinol. Cytochrome C is a small soluble protein that diffuses through the intermembrane space. Its heme C group carries only one electron at a time, allowing it to shuttle electrons individually from complex 3 to complex 4. Complex 4 is the final enzyme of the respiratory chain. Here, four electrons are ultimately transferred to molecular oxygen, reducing it completely to water. Each reduced cytochrome C delivers one electron to the copper A center, which then transfers that electron to heme A. Heme A serves as the final relay before electrons enter the catalytic oxygen reducing center. The first electron reaches heme A3. Although oxygen has not yet been reduced, this change in oxidation state is already associated with the movement of one proton across the membrane. The second electron reduces the copper B center. Again, proton pumping accompanies this electron transfer even before oxygen reduction is complete. Once sufficient reducing power has accumulated, molecular oxygen binds between heme A3 and copper B. A nearby tyrosine residue donates a hydrogen atom, while electron density weakens and ultimately cleaves the oxygen oxygen bond. The remaining two electrons complete reduction of the oxygen intermediates. Each electron transfer continues to be associated with one additional proton pumped across the membrane. Finally, four chemical protons from the matrix convert the two oxygen atoms into two molecules of water. Combining both pumping and chemistry gives the overall reaction shown below. Notice that not all matrix protons have the same fate. 4 become part of water, while 4 are transferred across the membrane to strengthen the proton gradient. Having established the proton gradient, we now turn to the remarkable molecular machine that converts it into ATP. ATP synthase contains 3 catalytic sites that continuously cycle through loose, tight, and open conformations. The proton gradient does not directly force ADP and phosphate together. Instead, proton flow rotates the central shaft of the enzyme, mechanically driving these conformational changes. ATP is synthesized in the tight state and released during the open state. We can now summarize the contribution of a single NADH molecule. Altogether, 10 protons contribute to the proton motive force generated by one NADH. Complex 1 contributes 4 protons and 2 protons stored temporarily within QH2. Complex 3 converts the stored protons into 4 protons within the intermembrane space, while consuming 2 additional matrix protons. And complex 4 pumps 2 more protons while consuming 4 matrix protons during water formation. Because ATP synthase requires approximately 4 protons per ATP synthesized, each NADH produces roughly 2.5 ATP. Electrons, however, entering through FADH2 bypass complex 1. Consequently, only complexes 3 and 4 contribute to the proton gradient, producing a total of approximately 6 proton equivalents. This corresponds to roughly 1.5 ATP molecules produced per FADH2 oxidized. Oxidative phosphorylation completes the story that began with glycolysis. Chemical bond energy was first converted into reducing power in the form of NADH and FADH2. That reducing power became an electrochemical proton gradient across the inner mitochondrial membrane. Finally, ATP synthase transformed that electrochemical potential into the universal chemical currency of the cell, ATP. Electron transfer, proton transfer, molecular motion, and ATP synthesis are therefore not separate biochemical processes. They are successive stages of a single continuous transformation of energy. Till next time, Crip.